So we continue our discussion on Fourier series. So we want to study how we find Fourier series of even and odd functions. It turns out that the Fourier series expansion of an even or an odd function may either take only the cosine part or sine part, respectively. So we start by reviewing our discussion on even and odd functions. So from your pure math class, how did you define an even function? When we say that a function f of x is even, when is f of x even? The function f of x is said to be even if for all x in the domain of the function so function f of x is said to be even if this condition is satisfied, that f of negative x is the same as f of x for all values of x in the domain of the function. So that's how we define an even function. And if we sketch the graph of an even function, it turns out to be symmetric with respect to y-axis. So that simply means that the y-axis is a mirror line for reflection of the curve. But then we draw some few sketch to illustrate that. So this is an example of a graph of an even function. And by the way, this is a curve of which function?
Cos theta.
Cosine, correct. This is a graph of cosine function. So cos function is an example of an even function. We can also give another sketch. So even if you have an arbitrary function whose graph may take this form, so provided that the graph is symmetrical with respect to x-axis, with respect to axis, not x-axis, then the graph is an even function. You can also have another sketch. So this is also an example of an even function. And another interesting thing is that if you integrate an even function between the interval minus alpha and positive alpha, is the same as twice the integral from 0 to alpha. That's what I'm trying to say, that, for example, if this point here is alpha minus alpha, and then this point is alpha, so if I integrate from minus alpha to alpha, is the same as taking the integral from 0 to alpha and then multiplying by 2, because this area and this area are actually the same. So the area So we are saying that if we integrate an even function in the interval minus alpha to alpha, then integral from minus alpha to alpha of f of x dx is twice the integral from 0 to alpha f of x dx. It's a very powerful result that will help us to simplify integration of even functions when we have interval defined as negative alpha to alpha. Then also let's briefly discuss about odd functions. How did you define odd function in pure mathematics? When do we say that a function f of x is odd? The function f of x is said to be odd if for all values of x in the domain of the function, f of minus x is negative of f of x. Graphically, an odd function will be symmetric about the origin. And if we integrate an odd function in the interval minus alpha to alpha, we get so here is a sketch of an example of an odd function. These are a graph of which function?
Sine.
Sine function.
Sine.
So this, yeah. So y equals to sine x is an example of an odd function. So what you're trying to illustrate here is that, for example, if I have my alpha, a negative alpha to be at this point, so this way I'm going to have my alpha. So you see there is this area 1, and there is this area 2. Area 1 is negative of area 2. So from minus alpha to alpha, I can move from minus alpha to 0, then 0 to alpha. So minus alpha to 0 will give me a negative area, then 0 to alpha will give me a positive area, which is exactly the same as the area from minus alpha to 0. So minus plus cancels out and we get 0. That would be very useful result when it will come to computation of Fourier series for a function which is known to be odd in a arbitrary interval minus alpha to alpha. So the result of such an integration will be 0. Also, another graph So this is another example of an odd function graph. We can also have so note that so 1, if f of x is even and g of x is also even, then the product f of x times g of x is also even. So this result is claiming that the product of two even functions is also an even function. So even function times an even function also produces an even function. Number 2, if f of x is odd and g of x is also odd, then if I take f of x, I multiply by g of x, I get an even function. So this means that odd function times an odd function always produces an even function. The product of an odd function and another odd function gives you an even function. Number 3, if f of x is even and g of x is odd, then if I multiply f of x with g of x, I get an odd function. So that's to say, even function times an odd function always produces an odd function. Then lastly, number 4, if f of x is odd and g of x is even, what do you think the product will give us?
Odd.
Will be an odd function, correct? So f of x times g of x will be odd. So always an odd function times an even function always produces an odd function. Leave one page or you will, in that space, you will prove this for results. So exercise, provide the proof of the above result. So this concept of product of even and odd functions will be very useful because if you remember the structure of the Fourier series, to find the Fourier coefficients, there is always the function multiplied by either cosine or the function multiplied by either sine. And we know that always a cos function is an even function, and a sine function is always an odd function. So if the oddness or evenness of the function post Fourier series is to be defined is known, then we can always determine the nature of the product of f of x and cosine of x or f of x and the sine function in the Fourier series structure. So the Fourier cosine and sine series. So what we call a Fourier cosine series is a series of a function such that after computation, the only trigonometric terms in the series are cosines. And similarly, a Fourier sine series is a series which only involves sine terms. So there are two cases to consider. We start by considering a function which is known to be even, and then see how its Fourier series looks like, and then thereafter discuss a function which is known to be odd, and see how its Fourier series looks like. So case one. Let f of x be an even function defined let f of x be an even periodic function defined in the interval minus pi to pi. So since cosine of nx where n is 1, is 0, 1, 2 up to infinity, is an even function. The function f of x times nx will be what should I fill in that space?
Even.
Should be an even function because the function already we have started by saying that the function f of x is known to be even. So this f of x is already even. And because a cosine function is always an even function, so f of x is even, cos of nx is even. So even times even is always an even function. So the function f of x cosine of nx will be an even function. So hence, an, which is given by 1 over pi minus pi to pi of f of x cosine of nx dx will be the same as twice 0 to pi of f of x cosine of nx dx. I think that should make sense from our other discussion when you integrate an even function from minus alpha to alpha. Is that true?
Yes.
Yeah. So because we are simply now from minus alpha to alpha for an even function, you now scale down your limit of integration from 0 to alpha, but then multiply by 2. So twice from 0 to pi f of x cosine of nx dx. Similarly, since sine of nx is an odd function, the function f of x multiplied by sine of nx will be, which type of function will be this?
Odd.
Will be an odd, because now we are multiplying an even function times an odd function. Remember, in this case, this first case, we are discussing f of x that is always known to be even. Now, when you multiply an even function times an odd function, we get an odd function. So the product f of x sine of nx will always give us an odd function. So therefore, hence, Bn, which is given by 1 over pi from minus pi to pi of f of x sine of nx dx. What will this give us?
0.
Correct. This will be 0 because we have known that whenever we integrate an odd function from minus alpha to alpha, remember this function here is odd. And whenever we are dealing with an odd function, the limits of integration are from minus alpha to alpha, we get 0. So therefore, this value will give us 0. So hence, the Fourier series of f of x known to be even is f of x equals to a naught over 2 plus summation n1 to infinity of an cosine of nx. So remember, the other term is usually bn a sine of nx, but we have already said that the bn value is going to give us 0. So 0 times sine of nx is just 0. So this will be the only terms that will be in that series, which you can write it as a naught over 2 plus a1 cos x plus a2 cos 2x plus a3 cos 3x plus a4 cosine of 4x plus other several terms. So this is what we call the Fourier series of the Fourier cosine series of the function f of x. So this is Fourier cosine series of the function f of x. I remember that f of x should be known to be even in the given interval in the problem. So it turns out that when you do the process of the Fourier series computation, the only trigonometric terms present will be cosine functions. And then remember, in this case, A naught will be given by 2 over pi 0 to pi f of x dx, and an will be given by 2 over pi 0 to pi of f of x times cosine of n x dx. So case 2, when the function f of x is known to be odd in the interval minus pi to pi. So case 2, we consider a function f of x that is odd and periodic in the interval minus pi to pi. So let f of x be an odd periodic function then f of x times cosine of nx will be an help me fill that space.
Odd.
It will be an odd function because already f of x is known to be odd in the interval minus pi to pi, and cosine is always an even function. So taking an odd function times an even function gives us an odd function. So this will be odd function. Then, so therefore, an, which is 1 over pi, from minus pi to pi of f of x times cosine of nx dx, with that in mind, that the product, this function here, is odd. What does this give us?
Zero.
It will be 0 because now we are integrating an odd function from minus pi to pi. There's the same case of from minus alpha to alpha get 0. So this will be 0, and remember n is 0, 1, 2, 3, etc. And then if we know that f of x is odd and sine of nx is also an odd function, then if we take f of x, we multiply by sine of nx, will be which type of function?
An even function.
Will be an even function because now we have two odd functions being multiplied. So odd times odd is even. So this product will give us an even function. So as usual, let's compute the Bn, or the coefficient Bn in the Fourier series. So Bn is always 1 over pi minus pi to pi f of x sine of nx dx. So what will that give us?
Two over pi.
2 over pi.
And
We
from
get now from
0
0
to pi.
to, yes,
To
the
pi.
same function.
Yes.
Correct. So this is what we have from what we have earlier on, or from what we have discussed earlier on the integration of an even function from minus alpha to positive alpha. So what is giving us this result is because this product is an even function. So remember, this holds for n from 1, 2, 3, up to infinity. So therefore, the Fourier series reduces to f of x. So remember, all the n from 0 to infinity are zeros. So the term a naught over 2 is not there. The term bn cosine of nx is not there. So it's simply summation n from 1 to infinity of bn sine of nx, since a naught and an, all of them are 0 from the previous computation. So which is the same as just saying that f of x is b1 sine x plus b2 sine of 2x plus b3 sine of 3x plus b4 sine of 4x plus other several terms. This is what we call the Fourier sine series. So this is what we call the Fourier sine series. Please, I have to caution you in advance. I have to caution you in advance so that you may not make mistakes. For instance, before you reach this conclusion that you are going to define a Fourier cosine or a Fourier sine series, note that the domain of definition of the function is very key. Domain of definition of the function is very key. In the conclusion, as to whether the given function is odd or even. For instance, if I give you a function f of x equals to x squared for all x in R, is this function odd or is it even? F of x equals to x squared.
Even.
This function is even because you can test that. So let me call this one. Here, f of minus x is going to give us minus x squared, which is just x squared, which is the same as f of x. So the function so you comfortably conclude that the function f of x equals to x squared is an even function for all values of x in R. So remember, this means for all. So f of x equals to x squared is an even function for all values of x in R, because when you say the domain of definition is real numbers, so they are negative real numbers and they are positive real numbers. So then the definition of an even function is satisfied because f of minus x is the same as f of x. Now, is f of x equals to x squared even on that interval minus pi to pi? Yes or no? Is it an even function in that given interval?
Yeah.
Yes or no?
Yes, it is.
It is, because if we say, for example, the function, the value of the function at minus pi, I'll have minus pi squared, which is pi squared, and then do the same thing as putting f of pi. So remember, pi is still in the interval. So yes, it is true that the function f of x equals to x squared is even on the interval minus pi to pi. Number 3, is f of x equals to x squared even on 0 to pi?
No.
This is not, the answer is no. Since you can't be allowed to define the values of f of negative to give f of x. So this interval here, there are no negative. So there are no negative arguments that will actually satisfy the definition of the evenness of a function on that given domain. So you have to be very careful before you start making a general statements or general assumptions that we always know that f of x equals to x squared is an even function. Be careful with respect to the domain where the x should be defined. So when they ask you to find the Fourier series of the function f of x equals to x squared on the interval, say 0 to pi or say 0 to 2 pi, please, you don't start now assuming that you are dealing with a cosine Fourier series, because what you did earlier on, you know that if you have x squared, then it's always an even function. That's not true. So before you reach that conclusion, ensure that you have tested that the conditions for oddness or evenness are satisfied within that given interval of definition. Small break, and then we come back to do an example.